Yeah, so I'm going to talk about planetary nebulae, which I think are some of the most beautiful and visually striking objects that we can observe in our universe. Stars are cool, galaxies are cool, but planetary nebulae are some of the best looking things to look up at and think about. So here are a couple, 20 I think, example planetary nebulae, and I'm going to talk about them, how they form, why they look the way they do, and how it relates to the end of our sun. So we have to first ask ourselves, what is a planetary nebula? Does anyone know?
It's like everything. It's like a white dwarf in the middle and then gases on the side.
Yes, that's 5 words. I'm done. I don't need to talk anymore. I really don't want to do this. Okay, so what is a planetary nebula? Okay. Okay, that's fine. So we have a planetary nebula right here on the right. This one's lovely named the Little Ghost Nebula. This image is from Hubble. You'll see that many of the images I'm going to show today are actually from the Hubble Space Telescope. In this image, it's colored so that oxygen, the element, is blue, hydrogen colored green, and nitrogen's red. So a planetary nebula is actually kind of named as a misnomer. So it's not related to planets at all. It's named this because I think it was William Herschel who first started observing these, thought they looked like little planets because he had just recently discovered Uranus. And he's like, oh look, these kind of look like planets because they're round and colored and you can see them like the actual round shape on the sky. What they actually are the last stages of dying stars that have masses about where our sun is, so 1 solar mass up to about 8 solar masses. And it is potentially the fate of our sun in about 5 billion years. And so you may ask yourself, well, our sun's pretty old. It does its shining business every day. Not lately here, apparently. I thought I got away from this when I left Boston, but nope. So how does a star die? And so we can actually see this kind of happening, not in real time, but we can look at large samples of stars, and we can see them in all different stages. And so we can see how they evolve, even though you can't for an individual star. And so when a star reaches what we're going to call the end of its life, where in its core it stops nuclear fusion, I won't go into all those details, just trust me, it stops fusion in the core, and it evolves. The outer layers of the star start to expand, and they can be blown away from the surface by a strong stellar wind. And so that wind carries the material away, and we can actually see that in some cases. So this is not actually a planetary nebula. This is the wind surrounding a red giant star that was observed by ALMA. And so you can actually see here that these are kind of rings of dust and gas that are being blown off of this star as it approaches the end of its life. And so we know that the star can expel massive amounts of material as it's evolving, and we can see these shapes as they're coming along. Eventually, with that wind carrying away so much material, the core of the star, that is the place where fusion had taken place, can be exposed. And so I have this little simulation. You can kind of ignore the blue box on the right. I can't get rid of that. We're really interested in this star here in the center. So in this animation, you're actually going to see a star that goes through what we call pulses as the envelope expands and throws off the material, contracts a bit, throws off some more material, and it goes through these pulses and expels more and more material. And you can see these kind of clumps here. This simulation is actually for a carbon-rich star at the end of its life, and as the material gets far enough away from the star, the carbon can condense into clumps and kind of form these knots and clumps of material that make the dust a little bit more opaque. Eventually, it throws off enough material, and we're going to zoom out here real quick, so you can see all this material that's been blown away from the star. The core becomes exposed, and the core, where the fusion happened, is so hot that the wind that I was talking about before is a lot faster, and it has a lot more energy, and so it ionizes, or basically it strips off electrons and heats up the material of that gas, blows it away, and you end up getting a planetary nebula. And in essence, that's all this is the wind expands from the star, all that material gets blown off, the core of the star is exposed, which is hot enough that it basically irradiates all that material, making it pretty. So basically that dust and gas absorbs some high energy, in this case usually really strong ultraviolet light, and then the material can re-radiate that out at lower frequencies. So think of it in the same way as like a black light. So if you've ever gone to like a party or a rave and there's black lights and stuff glows, it's basically absorbing higher energy UV rays and then emitting them in the visible so that you can see them. The same sort of principle in essence kind of applies here. So this was a simulation. It was actually the simulation of the birth of the Ring Nebula. Again, this is approximately true color. And so once the hot exposed core irradiates the surrounding material, is basically the planetary nebula stage. When I say hot, the core is approximately 200,000 degrees Fahrenheit or 120,000 degrees Celsius. So it's hotter than the surface of the sun because this is where fusion took place during the life of the star. The fast wind from the core is slamming into this slow wind that was from the envelope. So while the star was throwing off its envelope, that's like 10, 15 kilometers a second, which is only like 34,000 miles an hour. So slow, really slow. It's like driving on the 110 into LA. But that material is moving slow, but once the core becomes exposed, the core can actually radiate. The wind is less massive, so it's not as much material, but it's moving much faster with much more energy. And that's usually about 1,000 or so kilometers a second. So that's over 2 million miles an hour. So 1,000, 1,000, 1,000. You're roughly almost in New York now. So that's kind of how fast these winds are going. And so that's what kind of helps create these beautiful shapes. Because if you can imagine you have something moving slow, you have a slow moving gas, then all of a sudden you move a gas at 100 times the speed of that previous gas, it's going to catch up, slam into it, and kind of make these shocks and excite the material that we have. So you may ask, okay, why does the edge of the planetary nebula stop there? Well, that's actually just a consequence of looking in the visible range. If we move into infrared, for example with Spitzer, which is a space telescope for JWST, you can actually see there's actually a lot more material around this planetary nebula than that core part that you were seeing in the visible. And if we zoom out here a little bit, you can actually see there's a circular portion of the nebula that you can't see in the visible, and that's really showing you how far out these winds are extending. So earlier I had talked about these knots. So here's another example of the formation of a planetary nebula. So the wind is blowing off the envelope of the star, it's coming out. Eventually enough of the envelope has been ejected that the core is exposed, and that hot core will ionize the inner part of the nebula, making it beautiful and pushing things out. And what can happen is, as Dee was talking previously, sometimes things are clumpier in the universe. Same thing with winds. Winds can be clumpy too. And so with these clumps, they're not as easily pushed away by that fast wind. So the material around them gets pushed back, and that makes them more clumpy until you get these what are called knots, where the envelope is basically really clumpy and has been stripped away from the edges. So the simulation has actually transitioned into an image from Hubble of this object right here. This is the Helix Nebula. I'll talk a little bit about that in a second. So here you can see in the center where the central star now, the core, the planetary nebula nucleus, is irradiating in the envelope. And if we zoom in a little bit, which, sorry people down there, but you can actually see all of these really clumpy material, these clumps of the wind that have been pushed back and exposed because the wind from the star was actually kind of clumpy. So if we go through this, again, if we look into the infrared, we can actually see the clumps better in this case because the clumps are mostly dust. So this one image is from Spitzer, the visible that was previous is from Hubble. And so the basic process here is the star becomes a giant, that star ejects shells of gas and dust, kind of in pulses repeatedly, cyclically. This kind of shock front from the exposed core heats up the nebula, ionizes it. Little dense clumps form these knots at that front. Only the densest one survives, and then the rest are stripped away, and you kind of get these cool looking features. So this is one of the nebula that I showed you before. Now I'm going to show you a bunch of pictures because I don't like to write. So it's going to be a bunch of pictures, just to show you a little variety of what these are. So this is the Ring Nebula. They often have these unfun names like NGC 6720. That's the next generation catalog ID number. But most of these, because they have such fun shapes, are called things creatively like the Ring Nebula, because it's shaped like a ring. Wow, you guys are smart. Do you go to Caltech? Good. Yeah. So a lot of these are a couple thousand light years away. For example, this one's about 2,500 light years away. They're also really large physically across. So this one is 1.5 light years across. So that means it takes light 1.5 years to get from one edge to the other edge of the nebula. So they're actually quite large objects, mainly because these winds kind of are fast. Even the slow wind, 35,000 miles an hour. You know, over a couple 100,000 years, that can still go pretty far. Okay. The next one we have is the Helix Nebula. This one's actually really close. It's the closest one to Earth, 600 light years. And this one's even bigger. This one's 3 light years across. So they can be very large. This one's really pretty. Oh, this one, this is the better known name, the Helix Nebula. My favorite is actually also sometimes known as the Eye of Sauron. And then you can see why. Yes. So I vote that we push that name more than Helix Nebula, because that one doesn't really work. This one's known as the Little Red Spider Nebula. Pretty far at 5,000 light years, 1 light year across. This one's actually much different shaped than the ones you've previously seen. It only has 4 legs, so it's not really a spider. But none of us are biologists, right? Are you?
It looks like a neuron.
Oh, okay. We can call this one the Red Neurons Nebula. Okay. This one's actually really pretty, and we'll come back to this one in a bit. This is the Cat's Eye Nebula. If any of you have cats, maybe you know why. Yeah. This one, the constraints on the size of it, they say the core is 0.2 light years across. That's just because with this one, how do you define how large it is? Is it like these outer circular rings, or is it from tip to tip, or across here? So they just picked a spot and said it was 0.2 light years. So this one's really fun looking. Maybe we'll come back to this one. This one doesn't have a name. Some of them don't even have names. So, you know, yeah. Who wants to name this one? Yeah. This one's 14,000 light years away. So this is one of the further ones, and it's a light year across. It's kind of fun.
Onion ring nebula.
Yeah, the Onion Ring. This is the Retina Nebula, 2,000 light years away. So again, all of these images so far have pretty much been from Hubble, the Hubble Space Telescope. So these are all real objects. These are real images. If you had a powerful enough telescope from Earth, you looked, this is what your eye would pretty much see. The colors may be a little different depending on how they've colored these, but they're pretty much what they are in the visible. I'm going to stop naming them and start listing more and more at once. So here are different varieties of them. They're a little more blobbish here. These ones are also a little more blobbish, but some fun colors. This one's got a weird central kind of nucleus going on, then it expands out. Very fun. These 3 are all the same color, so that's boring. This one's kind of swirly, I guess. That one looks like an old photo, so not fun. Okay, I saved the 2 best for last. My 2 favorite are these 2. These are real images from Hubble. They're really, really pretty. Yeah, you can't, ChatGPT can't do this. Only the Big Bang could end up giving us this. So this one doesn't also have a name, NGC 5189, and this is the Lion's Mane Nebula. It's both about 3,000 and the Lion's Mane is 6,500 light years away. So this one's great because it's very asymmetric, very irregular. I think they released this around Christmas, X number of years ago. They called it the Ribbon Nebula because this was supposed to be like a Christmas ribbon. They must be more creative at NASA than I am. But it's very beautiful. It was my wallpaper for a while. And the Lion's Mane is really great because you can actually see all of those knots going around the edge, and you can see them being blown out radially, so away from the central star. Actually last now, is the Butterfly Nebula, NGC 6302, 3,500 light years away, 1.5 light years across. So I'm just going to take that off for a second and look at this. So we looked at all of these. Does anyone have a question they might want to know? Yeah.
Okay, so they're saying the sun will die in 5 billion years. Do you think it'll be sooner than that? Or the sun turns into pretty giant, maybe in a billion years?
No, it's pretty well known. We understand pretty well how the lives
Or
go.
it be uninhabitable by that time?
There's other questions that might lead to that. Yeah. So what about planetary nebula? Anyone have any questions about what we've seen? About why? Yeah. They're what?
What causes them to take different shapes?
Exactly. Thank you. Did you look at my slides beforehand? No? Okay. Why are they such crazy shapes? You know, we started with the Ring Nebula and the Helix Nebula. Okay, they're kind of round. They were blowing off from stars. Stars are circular. That makes sense. But with this? A star made this? Yes. So there's actually a few different answers to this question. One, the simplest, is something that you could think about as projection and viewing angle. We're looking from our point on Earth at these objects. But in space, these are 3D objects made by 3D stars. They have some spatial composition to them. And so for the Ring Nebula, if we bring ourselves out to the universe's point of view, we can see something that actually looks more like this. So what I just showed you, how we really see it, would be if you're looking down from the top of the screen into this object. So there's a 2 observer line here. So we're looking down into this object, and we're seeing this torus, this equatorial plane, where all those knots are. So we're looking through this kind of halo, through some features, into this torus, into where the central star is. So if we were to rotate and come out and look from this angle, what we would see would look entirely different than how we see it. So maybe projection and view angle is kind of what we see. An example of this are these 2 objects, a planetary nebula IC4406 and NGC 2392. These are 2 different objects, yes, but physically they're both basically the same, except one we're seeing on the edge, so we can see the long part, and the other one we're looking down the barrel, like if you were to hold a pencil and look right down it. So we can see they're basically the same, except our viewing angle has changed. So that can explain some of it. Not all of it, though, especially for some of those crazy looking ones. Why aren't they spherical? You know, okay, I get the viewing angle part, but why is that one long anyway? Why is it not a sphere? Some people say asymmetric winds. So you can see here from earlier this wind, you can kind of see the spirals and rings. That can lead to some of it, but not a lot. It's not very fun, so we'll move on. Binary stars. This is something I'm particularly interested in, and it actually can explain a lot of these planetary nebulae shapes, but not the purple. You guys pick bad seats. You'll know next time. Sit down there. And this is actually a JWST image of the Southern Ring Nebula using the NIRCam instrument. And so you can see here, kind of, in the middle is the planetary nebula central star. Wow, I'm magic. Thank you. Dinner and a show. Yeah. So you can see it's ionizing the central part of the nebula, and then it's expanding out, and we get this nice shapes. Well, if you look further into the infrared using the MIRI instrument, you can see that one central star, bam, it's actually 2. There's 2 stars there, and they're in a binary pair that are orbiting each other. And so when 2 stars orbit each other, they can interact, and they interact with each other's winds and envelopes and all sorts of things. And so that can actually lead to the shape of these planetary nebulae. So here's an animation of a simulation of where we have a more massive red giant star around a hotter, in this case it doesn't matter what it is, but basically it forms a disk, and then from this disk you can eject jets. So these are basically very collimated, they're very straight lines of material that are flowing out very fast from this disk. And so if I play this, you can see that it can spin, and the disk can precess, which means it goes like this. And as it does that, the jet can swirl into cones, kind of like you're at a party and you're jump on it, yeah, no? And as it does that, it shoots out these jets. These jets move very fast, hundreds of thousands of kilometers a second, and they can impact the environment around it. So if we zoom out here, these are kind of helical, they're spinning spirals, because that jet is what we call precessing, which means it swirls like this. It's spinning, but then it precesses like that. And you can end up with these kind of conical spirals out. What? That disk is because matter from one star is flowing onto the other, and it has to spin because it's getting closer, so angular momentum means it has to spin faster as it comes into the disk. In the center of it. So, yeah. For our purposes, it doesn't matter what type of star it is, but it is a star. And so that's actually how the Cat's Eye Nebula got its shape. There's a binary central system in there that shot out jets and made this great, great shape. So I'll show that here. So there's two stars in the middle. They must have at some point thrown off a lot of their envelope, exposing the cores. And there's some disk, and that disk made some jet. And we have the rings from the envelope. But as those jets come out, they run into the material and they have to like punch their way through, and they make these shocks and they clear out the cavity that makes the Cat's Eye Nebula. So that's kind of how this one formed. So if we go back to the Hubble image, you can actually kind of see the jet material coming out right there from the plane of the central star system. So that's almost the end of the road. So these are hot objects in the core. The central star is very hot. It's ionizing the material. But it can't stay hot forever. It's radiating energy, so it starts to cool. The central star starts to cool, the envelope keeps expanding. At some point, it becomes too cool to ionize that material, and so it no longer glows invisible. So they expand, they cool, they fade, they slowly fade away to never be seen again. And that happens in 10 to 50,000 years. So very short. 50,000 years from now, all the planetary nebulae that we know are gone. That material continues to move off into the interstellar medium, eventually becomes part of star-forming nebulas, and then gets mixed into new-forming stars. And so the elements in your body, your carbon that you're made out of, came from a planetary nebula at one point, and eventually will likely return there again.
What happens to the...
Yes, I'm done.
What happens to the white dwarf?
What?
What happens to the white dwarf?
Yeah, so the central star cools, and it becomes what's known as a white dwarf, and that continues to cool, and it continues to cool, and it continues to cool. For billions of years, it just cools until it becomes what theoretically would be a black dwarf, because you just can't see it. But it stays there, just slowly cooling. It depends on what you mean by star.
How cool is it?
The white dwarf? Oh, well, we know white dwarfs now that are 100,000 Kelvin, and we know some that are like 3,000 or 4,000 Kelvin. So fairly cool, like very, very, very cool. That have cooled over billions of years.
Will it ever get cool enough that I can stand up?
I mean, so the surface of a white dwarf is fairly solid, but the gravity is so high that you wouldn't stand. You'd become a pancake, basically, yes. Yeah.
Okay, thank you. That was such a good talk. I was wondering, you had mentioned that in one of the pictures that the winds were moving at an immense kilometer per second. How is that measurable?
Yeah, so we can do something called spectroscopy, where if you guys, prisms, like the, is that an AC/DC album? Pink Floyd, I'm sorry. Yeah, so if you shine light through a prism, it breaks out into the rainbow. Well, that's because it bends differently depending on the wavelength or the color of light. And so we do something slightly fancier, not always, with starlight. So you can take the light from a star, pull it in through a big telescope, break it up amongst all of its wavelengths, and you can look at all the different wavelengths. And since we have labs here on Earth, we know what elements basically emit at what colors, what wavelengths, and so we know when they're not moving where those wavelengths are supposed to be. And when material moves and emits light, it is what's called blue shift or red shift. It's like the Doppler shift. It's the same reason when like a fire truck goes by, it sounds louder and higher, and then it goes by you when it's lower pitch. So light does the same thing. It's red shifted, which means that the wavelengths get longer, or blue shifted, which means they get shorter. And so we can actually measure that, and that directly tells us the velocity, the speed of the material that's emitting that light. So we can actually just take observations of the different parts, and we can measure how fast they're moving, and then in what direction. Yeah. It's one of the easier parts, actually. Yes?
Can you explain why the term planetary nebula came to be, since they don't have anything to do with planets? What was the understanding when it was first discovered that led to that terminology?
Yes, so there's two answers. One is the short that you can almost always give in astronomy, is that some old guy thought something, named it, and then no one's ever changed it since. And so that old guy was, I think, Frederick William Herschel. And basically, he had just discovered Uranus, and he was looking up in the night sky, and he saw these smidges and blobs that were round, and he's like, oh, they kind of look like planets. But they're too far away to be planets. But I'm going to call them planetary nebula, because they're very nebulous, or thin and like wispy. Planetary nebula. They look like planets, and they're nebulous. That's the story. Yeah.